Okay, so we're in chapter 7 now. Chapter 7, kind of like chapter 5, is only 2 sections for us. There's more sections in the chapter, but we only need to cover the first 2. So in this section, we're going to be talking about something called orthogonal matrices. The definition of an orthogonal matrix is this. It says that a matrix A is orthogonal if the inverse of A is its transpose. Notice this definition would only apply to square matrices that are invertible. So it's impossible for a square matrix to be orthogonal if it's not invertible. It's also impossible for a non-square matrix to be orthogonal. Pay special attention to this. We're using the term orthogonal differently than we did in the previous section. There is a relationship and there's a reason why we call it orthogonal. But make sure you understand the difference. This is different from talking about 2 matrices in the space MNN being orthogonal to each other in some inner product that was defined on that space. This is a property of just a single matrix. So to illustrate this, let's go through an example. We want to show that this matrix, cosine of theta, negative sine of theta, sine of theta, cosine of theta, is orthogonal for any choice of theta. Now this is actually a very important matrix. We haven't covered section 1.8 all the way back in chapter 1, but if we had, we would have talked about matrix transformations, and probably would have talked a little bit about some of the geometric implications that those have on vectors. This particular matrix is what we call a rotation matrix. If you read through section 7.1, it'll talk about this in more depth in a couple of examples. But the idea is if you take this matrix, and then if you pick a vector in R2, represented as a column matrix, and multiply this on the right by that vector in R2, then what it does geometrically to the vector that you're multiplying it by is that it rotates it by an angle of theta. And we could show that, we could prove that. It's a really useful application of this particular matrix, but I'll let you look at the examples in the book if you want to get more information on that. Our goal right now is just to show that this is orthogonal for any choice of theta. The way that we do that is we need to show that the inverse of this matrix is the transpose of this matrix. Now, you could go through the process of using the inversion algorithm or whatever, to show that this has an inverse that's the same thing as its transpose, but we could just use the definition of an inverse also. If I take this matrix and I multiply it like this, so here's the original matrix. If I multiply it by its transpose, and notice the transpose is actually just going to trade this minus negative sine of theta for this sine of theta. So I'm going to still have cosines of thetas on my main diagonal, but then I'm going to have a sine of theta here. This will be a negative sine of theta, and that's a cosine of theta. Okay? So the 2 by 2 matrix that I'm going to get from this, it's cosine of theta times cosine of theta plus negative sine of theta times negative sine of theta, which is cosine squared plus sine squared of theta. And then over here, if I do sine times cosine, cosine times negative sine, I'm going to get cosine of theta sine of theta minus sine of theta cosine of theta. Over here, if I multiply this column by this row, cosine sine minus cosine sine. So I'm going to have cosine of theta sine of theta minus sine of theta cosine of theta. And then here, sine times sine, cosine times cosine. I get sine squared plus cosine squared. Notice these 2 entries are going to come out to 0, and by the Pythagorean identity, these 2 entries come out to 1. So I get 1, 0, 0, 1. The identity, the 2 by 2 identity. That would imply that these matrices are inverses of each other, but I simply took the transpose of this matrix to get that inverse. So that would imply that this is an orthogonal matrix. Okay? All right, so that's actually the only really concrete example we're going to do in this section. The rest of this section is going to be focused on developing a lot of theorems surrounding orthogonal matrices, a lot of very useful theorems. So to start with, This is sort of an equivalence theorem. It's not the equivalence theorem. It's just a theorem that lays out three equivalences. So the following three statements are equivalent for every n by n matrix A. If A is orthogonal, if and only if the row vectors of A form an orthonormal set in Rn under the dot product, if and only if the column vectors of A form an orthonormal set in Rn under the dot product. To prove this, we're not going to prove it in its entirety. We're going to prove it the way that the book goes about it. We're simply going to show that A and B are equivalent, just because the equivalence of A and C is a very, very similar proof. And if A and B are equivalent and A and C are equivalent, then B and C would automatically be equivalent. So really, the gist of all of this is wrapped up in this proof right here. Okay, so what we're going to do is we're going to represent the rows of A as R1, R2, R, all the way down to Rn. Now, it gives you a description here. So if you take the transpose of a matrix, remember that what you're doing is you're changing the rows into columns. So if R1 is the first row of A, then R1 will also be the first column of A transpose. Similarly, the first row or the second row of A will be the second column of A transpose. And what we're doing here is we want to look at what happens when you multiply A to its transpose. This is a version of matrix multiplication that we looked at a while back. If you're multiplying two matrices together, then the ijth entry of the product is going to be the ith row of A dotted with the jth column of that second matrix here. So by dotted, I mean the dot product of this row, the ith row with the jth column here. So using what we know about the rows and columns of A and A transpose, this matrix is what would result from taking this product. Now, here's where we use the assumption that A is orthogonal. We know from orthogonality that A times A transpose will equal the identity matrix. So this thing should come out to the identity matrix, but what that's going to mean is that any main diagonal entry is equal to 1. R1 dotted with R1 is equal to 1. R2 dotted with R2 is equal to 1, and so on and so forth. In other words, every row of A, when dotted with itself, is going to equal 1. What that means, remember, when you dot or when you take the inner product of a vector with itself, and the dot product is an inner product, what you get is the square of the norm of that vector. So that's telling us that each of these rows, R1, R2, all the way through Rn, has a norm of 1. Remember, that's part of what you need for an orthonormal set. In addition, because this is the identity matrix, any entry that's not on the main diagonal should be a 0. That's what makes that an identity matrix. But if you look at the entries that are off the main diagonal, they're always of the form of a row of A dotted with some other row of A. If those are all equal to 0, then that means every row of A is orthogonal to every other row of A. And that makes the rows of A an orthogonal set. But if we use the fact that we just established that the vectors, the row vectors of A are also all unit vectors, then that means the rows of A form an orthonormal set. You can construct that argument as a sequence of if and only if statements, which is done here. So that actually establishes the equivalence, that A is equivalent to B. It establishes the if-then in both directions. Okay? So an interesting way of looking at that. But if we go back here, we can verify that. Look at the rows of this matrix. We showed that this is orthogonal just by using the definition of orthogonality. But the rows, if you consider them as vectors, are going to form an orthonormal set. Notice if I dot this with itself, I'm going to get cosine squared plus sine squared. If I dot this with itself, sine squared plus cosine squared. The rows have a norm of 1. What if I dot this row vector with this row vector? Well, that's cosine times negative sine plus sine times cosine, which is 0. These two rows are orthogonal to each other. So we can see that in that example. All right, let's go ahead and move on. We're going to talk about another theorem here. Like I said, that from here it's kind of just unloading a lot of theorems that we need. There's going to be a little bit more in the way of examples and work that we do in 7.2. So this theorem is just some properties of orthogonal matrices. Let's suppose that A and B are both n by n orthogonal matrices. Then A inverse is orthogonal, and that actually just follows straight from the definition of what an orthogonal matrix is. The product A times B is going to be an orthogonal matrix as well. And in addition to that, the determinant of any orthogonal matrix is equal to plus or minus 1. Okay? So if we keep that, if I could prove any one of these are all very straightforward to prove. I'm just going to prove B. One thing that we could say about this property is that the set of n by n orthogonal matrices is closed under multiplication, meaning if I look at the set of all n by n orthogonal matrices, pick any two of them and multiply them, the result will be another matrix belonging to that set of orthogonal matrices. That's basically what B is saying. So to prove B, again, let's assume that A and B are n by n orthogonal matrices, which means that A transpose is the inverse of A, and B transpose is the inverse of B. What is it that we want to show? Well, in order to show that AB is orthogonal, I should be able to multiply AB to its transpose and get the identity matrix. That would show that these are inverses of each other, which means AB is orthogonal. So I'm going to start with this. Use the fact that we came up with back in chapter 1, which says if you want to take the transpose of a product of the form A times B, it's the same thing as the product of the transposes, but in reverse order, B transpose times A transpose. Okay, now because B transpose is the inverse of B, then B times B transpose is the same thing as B times B inverse, which is the identity matrix. So I get A transpose. Of course, the I here can go away. It's like multiplying by 1. And then A times A transpose, again, because A transpose is the inverse of A, would be equal to the identity matrix. So that shows that the transpose of AB is the inverse of AB, which makes AB an orthogonal matrix. Okay? Yet another theorem. This theorem is going to be really important. At the very end of this section, we're going to talk about a theorem concerning change of basis. Remember in chapter 4 we talked about change of bases and transition matrices that take you from one basis to another. In particular, the theorem is going to concern what a case where the transition matrix is an orthogonal matrix. We're going to use this theorem in that proof. So pay close attention to this. In particular, we're going to use the equivalence of A and B in that proof. So this is another equivalence theorem with 3 statements that are all equivalent. They are A is orthogonal if and only if the norm of AX is equal to the norm of X for every X in Rn. And I want to be careful with this because remember the norm of a vector is always relative to its inner product. So this here, when we talk about the norm of X and the norm of AX, remember both of these X's are both of these vectors that I'm taking norms of would be vectors in Rn. And anytime we're not specifying what the inner product is on Rn, we assume it's the Euclidean inner product. That's the dot product, just another name for the dot product. So what I'm saying is that the Euclidean norm, which is the norm induced by that dot product, is the same if we multiply X by an orthogonal matrix as if we just take the norm of X by itself. It's not saying that AX is equal to X, but it's saying that these two vectors will always have the same norm for every vector in Rn. This is equivalent to this statement. Again, if I take any two vectors in Rn x and y, and if I multiply them to the orthogonal matrix A, and then I take the dot product of the resulting vectors, the result is the same as if I had just taken the dot product of x and y without multiplying them to A first. Okay, these end up being really, really useful properties or equivalences for orthogonal matrices. The way we're going to prove this one is kind of like how we proved the equivalence theorem the first time we encountered it, in kind of a cyclical way. I'm going to prove that A implies B, B implies C, and then C implies A, which sort of completes the loop. Okay? So in this proof is going to utilize some formulas that we came up with quite a while back, all the way back into chapter 2, specifically section 3.2. You'll see this proof came straight out of the book, and it'll reference the formulas and the sections in which they're found if you want to go back and look at those. But we talked about them a while back. I'm just going to go straight to it here. So A, we're going to assume is orthogonal. We're assuming A, and we want to prove B. So the property of orthogonality for a matrix means that the transpose of A is its own inverse. That would mean A transpose times A is the identity matrix. Okay? Now, if I think about what we're trying to prove, we're going to let X be any vector in Rn, and I want to multiply A on the right by that vector as a column vector. So Ax, the norm of Ax, and this is the norm induced by the dot product, is equal to this. This is the definition. Remember, the norm is equal to the square root, that's where the 1/2 power is coming from, of the inner product of this vector. So Ax dotted with Ax to the 1/2 power. Going from here to here is where I use a formula that we encountered way back in section 3.2. We showed that this dot product can actually be expressed this way. If I take A transpose A, which would be in another n by n matrix, and multiplied it on the right by x, and then I took the dot product of x with that vector, it's the same thing as this. So the purpose of representing this way is that we've shown up here by our assumption that A transpose times A is the identity matrix, which means A transpose A times x is really just x. This becomes the dot product of x with itself to the 1/2 power, which by definition is the norm of x. So this actually establishes B, because the norm of Ax for any x is equal to just the norm of x. Okay, moving on. Now if we assume B, we'd like to show that C is true. So here what we're doing is we're assuming that the norm of Ax is equal to the norm of x for every x, every vector in Rn. Okay, and again, we're using a formula that comes out of a theorem from way, way back in chapter 3, section 3.2. You may remember this one. We haven't really used it until this point, so you might have to go back and look at it. But if I have Ax dotted with Ay, we showed back in 3.2 that you could represent that dot product with this kind of funky looking formula right here. 1/4 times the norm squared of Ax plus Ay minus 1/4 times the norm squared of Ax minus Ay. Okay? Now, inside these norms, I could use the distributive property to factor the A out, which I'm doing here. Okay, you see the A has been pulled out. And this is where we want to use our assumption, because if x and y are vectors in Rn, then their sum would of course also be a vector in Rn, same with x minus y. But the norm of A times a vector in Rn, according to our assumption, is equal to that same norm of just the vector by itself. In other words, we could delete the A in the next step in both of these norms, giving me this. After getting rid of that A, this is the same formula we had up here, but for the dot product of x with y instead of Ax with Ay. So that establishes part C. Okay? This is like kind of the one place where we really want to use these funky formulas from way back when. All right, now finally, we're going to assume C and show that A is orthogonal from that assumption. And this is, I think, my favorite part of the proof, because it's not counterintuitive necessarily. It's just, I don't know, there's something about it that I like. So we're going to assume that for every x and y in Rn, ax dotted with ay is equal to x dotted with y. That's what C says. And again, for every x and y in Rn. So once again, citing that formula that we used up here from section 3.2, the dot product of x and y can be represented this way: x dotted with A transpose A times y. This whole thing is one vector, and x is being dotted with that. Okay? And it says here, this can alternatively be written this way. Now, if you're not seeing it, what happened is we can subtract x dotted with y over here, and I have a difference of two terms where there's a y present there. Where there's an x in the first, x is the first vector that we're dotting, so x dot something, okay? Remember, the dot product has the distributive property, so if we factor that x out, then this is what's left in parentheses, okay? Similarly, we can also pull this y out of here, because this is a difference of two matrices, specifically two column matrices, and matrices also have the distributive property, so the y can be factored out of that, giving me this: x dotted with the matrix A transpose A minus the identity I times y, and that's equal to 0. Okay, now remember, I've already emphasized this once, but this is true for every x and y in Rn, and more importantly, it holds for any choice of x in Rn. So in particular, if I set x equal to this other matrix right here, A transpose A minus I y, for whatever the choice of y was, then what I could say that that vector dotted with itself, which we're seeing right here, is equal to 0. But we know from the positivity axiom of inner products, anytime you take an inner product, in this case a dot product, of a vector with itself, if the result is 0, then this thing had to have been the 0 vector to begin with. That's a property that every inner product has to have. So that's what is being stated right here. Now, remember, again, emphasize it again, this whole argument was true for any choice of x and y. So if that's true, then this statement would have to hold even if y was a non-zero vector. In fact, if this is true for every choice of y, then the implication is that this matrix on the left has to be the 0 matrix. A transpose A minus I is the 0 matrix. But if I set that equal to the 0 matrix and add I to both sides, that means that A transpose A is equal to I. That means A transpose is the inverse of A, which makes A an orthogonal matrix. In my mind, that's a really cool proof. I like that one. It's not an easy one to come up with, but if you go through it and understand it step for step, it's a really interesting application of a lot of kind of bizarre formulas that we came up with earlier on in this course. Okay, there's more to talk about, but we'll wrap everything up in the next video.